Greetings and welcome back to a new video about system identification, and this is our example number 2 about the first order system. Again, we will look at calculations and simulations in MATLAB to verify our calculations. So let's look at our example. What we have is the following situation. We have given a unit step response of a system, that is this plot on the right side, and we would like to determine the transfer function of the system given this unit step response. So this curve is the response of your system at the output, and the input is a unit step. That means the input value, it is a step input, has an amplitude of 1 and it stays that value forever. So that's our input. So how do we now determine the response from this response, the transfer function of the system? So let's look at our solutions. As we did in the previous video, we need to make an observation from the plot, so we need to use the curve or the response in this graph. So let's look at the observation from the graph, and we need to use the output for that. And if I look at the output, I make the following observation. The slope starts with a value of larger than 0, so it is a non-zero slope, which is positive, and this shape is very similar to a first order system. If this slope was 0, so it started at 0 and then gradually go up or go down, doesn't matter, that might be a second or higher order system. So in this case, because this is a slope which is larger than 0, and it will then curve and settle to a value which is a final value, in this case 4, I estimate most probably it will be a first order system. That's actually where we're heading. Now I also see from the graph that the steady state value or the final value of our system is 4, so that's actually what we also see here from the plot very directly. I need an additional information, so I will then select the point from the graph. So I will now select the point here, which will be probably most easy to read. So I will take the point here, so I will make a 0.2 seconds. I will look at 0.2 seconds, draw a vertical line, and I will see the intersection with my graph, and that will give me this at 0.2. I have 2.25 as the amplitude, and I will need that. So the value of 2.25 at 0.2 seconds. That's actually what I have now for the output. So again, to memorize the situation for the transfer function model for a first order system, if this was of course an all-pole first order system without a 0 or a delay, I can use the following model, which is then given by h is equal to kdc, which is one of the parameters of your system, over 1 plus the tau s. So I have two parameters which will need to be determined. The first one, the kdc, is the steady state gain or the dc gain, and the second one, the tau, is the time constant, which is given in seconds. So the dc gain again is not the dc value of your response, it is a gain which must be of course related to the output divided by the input. So I have a steady state gain, it is not the steady state value for all cases. We will look at that in more detail. So let's then look at specifically our transfer function for the system. So the first one, the steady state, the DC gain for the system, that will be determined by using the steady state value of the output divided by the steady state value of the input. So it's output divided by the input. That is 4 over 1. So I know that the output has a steady state value of 4, but input has a steady state value of 1 because it is a unit step. Then I have 4 over 1, which is just 4, very straightforward. Okay, then the next one is the following observation. This is a general form of the first order step response. That is this formula, which will be used now in this case. What we see is the following: the response, just in time domain, is given by the final value or the DC value minus, between the parentheses, the DC value minus the initial value, this is the initial value, times the e to the power minus t over tau. So I have actually three parameters here: the DC value, final value, the initial value, and also the time constant. And this time constant, of course, we will also require in this transfer function. Now I have, of course, a value, this value from my plot, so I will use this also in this formula. So let's look at it, what we can do. Now, substitute the selected point. I've just selected, of course, this one. You can also take another one. For example, that's 0.5, approximately 3.4, maybe 3.5. You do it a little bit crudely. So it really depends on what you take. But I have, of course, the value of this one. And I also know that the steady state value is 4. So if I just substitute here the 4 and also the 4 here, I have then the following situation and also the selected point. So I have now at 0.2, I have 2.25. That will of course then make this expression the final value minus the final value and the initial value, and the initial value is 0 here. So that's actually also what we can substitute in it. Then I can substitute the time, which is 0.2, and over tau. So this is now the unknown we need to determine. It must be, of course, equal to this expression, must be equal to 2.25. So again, this is just substitution of the 0.2 for t in this expression, and we have this one. I need to, of course, substitute here also a 4, so that will be done in the next step. I will just give it in a formula form. Then you can see in the next step that this is just 4, this is also 4, so I will just make the expression. So I have now isolated in several steps. I've skipped those steps. You can see that the tau, which is the time constant, is then given by this expression, which can be done, of course, straight after a couple of steps, which is, I think, really straightforward. So I've just left the details out. And tau now is just substituting for this 4. I have then approximately 0.242 seconds. It's now 242 milliseconds. That's actually what I have for the tau. So I have the KDC 4. I have my tau 0.242. I can now set up my transfer function. So that is actually what I require to have. So having calculated all the required parameters for the transfer function, I have done the following. So this is exactly what we had in the model. 4 over 1 plus the 0.242 as, or if you want to see the pole directly, you can divide out the numerator and denominator by 0.242. Then you will have this expression. You can see directly that the pole is at minus 4.13. That's actually what we have here. Now, we will of course verify this in the simulations. So let's look at the next steps. So what we have is in the following situation, we need to determine the transient response. In this case, is the step response, and we will look at the situation now for our case. So let's look at the situation what we have here. So that's the unit step response. What you see here is then the curve, the output for a unit step response. We have a value here at 0.2, and you can see it is 2.25, exactly what we have used, also determined from the plot. And you can also see that the final value is 4, so those are all correct. And this is actually what we had as the plot. So we had the plot, we have determined 0.2, at 0.2 seconds was 2.25, you can see that also from here. And that was the transfer function. And you can see this and the final value are all matching our graph. So we can see from the step response, in this case the unit step response, that this is correct. Now that's fine, so we have actually met or verified our calculations using simulation. But let's also look at a body plot for this system. What you see is actually the following. You have a label here which is at 0.01. That's approximately DC, and I read here 12 dB. So we can see that is one of the points, and you can also calculate that by the DC gain in dB is given by 20 log of the DC gain as a scalar. That will give you 12.04 dB. So the actual value is 12.04 dB, but the MATLAB gave, of course, at this frequency it's not 0, 12 dB. So this is what we have. And in order to calculate the cutoff frequency, I have to go 3 dB, approximately 3 dB down. It's a little bit closer to 3.01 dB. If I go down from this value in a little bit more accurate way, 12.04, and I will go down 3.01 dB, so I will do 12.04 minus 3.01, I will have 9.03 dBs, and I will look at my frequency, and I can see it is 4.13 radians per second. That's actually what I had as my pole. So my pole of my first order system is directly also my cutoff frequency, or the bandwidth in this case, because it is a low pass filter. What you also see is the phase is minus 45 degrees at exactly the same frequency. So that's actually also characteristics of a first order system, that the cutoff frequency will be at the phase shift of minus 45 degrees. That's actually a verification for your situation. So that's all fine, and we have now verified that this also in the body plot. So you have now seen the simulation results in the transient response and also in the body plot, and that's a confirmation actually of our calculations. Now what we now do is next we will look at a MATLAB, and we will do that also in MATLAB in real time. So next step is going to the MATLAB. So let's do that. So we are now at MATLAB. We have again our script. This is the system identification example number 2. I have again defined a Laplace parameter as shown here. S is equal to transfer function of an S. So I have a parameter I can use in my transfer function. But I have also the parameters of the system. It is a KDC was 4 in this case, and I have a tau, which is the time constant in this case 0.242. And the model again for the first order system is KDC over 1 plus tau S. That's actually what we have. So what I need to do is now check the unit step response and also the body plot. I have already done this, of course, but now we will do that in real time. So let me check the H. So first run, of course, this, because that's what we really need. So run this, and I can see it is running. I will do that H is equal to, now I can see that this is 4 for the DC gain and also the time constant. I can also do that in the zero pole gain format, which is then equal to 0 pole gain format. And you can see directly that this is 16.53 approximately, and you can see the pole at S plus. You can see the denominator, which is then S plus 4.13, and you can see directly the pole is at minus 4.13. Now what I do now is step. So I will do step H, and then I will do the grid on. You can see directly the curve. Now this is what we have. So let me make it larger. And again, you can see if I do the steady state value, it is indeed 4 as we have determined, because that's actually what you also see here. And if I want of a new point here, I can just go to 0.2 and I will then see 2.25 according to our calculations. So I will do that, and that's actually what we have. So let me make it larger. This is indeed according to our calculation. So this is correct, and also the final value, which is also seen as 4. So that's all fine. Now let's also look at the body plot. So body of H and also grid on. This is the body plot. You can see the grid on. So we have the gain and also the phase. And you can see that the value here is approximately 12 dB, which is of course not exactly DC, but very close to DC, very low. And if I go down with my frequency, I mean with my gain, to 3 dB lower, approximately at 9, or actually 9.03, because that was actually what we have calculated a little bit closer. So I have then approximately this value. Let me go to the approximately this. Yes, this is actually what I have. So let me make it larger. And this is also what we have determined. So you can see this 12.04 actually in theory, but it's just actually at 0.1 radians per second. It's still not that value. So if I go down by 3.01 dB, I will have then this value, and this is the frequency, and it's also the pole frequency. You can see that also here. This is the pole frequency. You can see that from this expression. And I need to verify this also using the phase. You can see that at minus 45 degrees, I have the same frequency, let me also make this larger. You can see that same frequency, same pole frequency, I have a phase shift of minus 45 degrees because this is the first order system and low pass without a zero, and you will have this value for the phase. That's now for our second example about first order system where we have the unit step response and we have determined the system transfer function. Alright, that was for example number 2 again. We will continue with another example with different characteristics and different responses and also different topics. So keep in touch, and if you have any questions or comments, please let me know. I see you next time, and take care.